Okay, so yeah, thanks for the introduction. It's really nice to see that there are so many people here that are interested in scientific computing in Rust. I'm just going to make this into a big screen. Okay, perfect. Okay, so today I'm going to talk about Bernstein and Bézier finite elements for the relaxed micromorphic model in Rust. I'm just going to do a very small introduction of the relaxed micromorphic model because we don't have much time. As for me, I'm a postdoc at the University of Luxembourg, and this work came to be during my PhD in Dortmund. So, okay. So first, the problem, the relaxed micromorphic model, it's an enriched continuum model, so it has additional degrees of freedom. It can describe more complex kinematical phenomena. It's well posed in the space H1 cross H curl, and we can have a conforming discretization using Bernstein Bézier elements and Nédélec elements. Bernstein Bézier elements have optimal complexity. You have the Duffy transformation. That means you can transform them into a multiplication of univariate base functions. This is optimal. And we have also recursive evaluation for them. This is the Duffy transformation. And due to these univariate base functions and the fact that we have a recursive evaluation of them, we can also use dual numbers for automatic differentiation. And this is ideal. This is optimal because we have only one input and we are looking only for one output. So we do that and we get the value and the differential at the same time. So Nédélec elements can be used using some methodology that we introduced called the polytopic template methodology. We multiply these Bernstein-Bézier polynomials with a preset template of vectors, which these are, for example, the Bernstein-Bézier polynomials, and these are the vectors to create Nédélec elements which are H-co conforming. And by doing that, we get also the optimal complexity for the Nédélec elements. So let's talk more about the implementation itself. We introduce for that, this is HBFEM, so we use polynomial powers that range from the power 0 to the power 10, for example, power 1 to 10, and we wanted an efficient data structure for it. So we introduced here a new type of compressed sparse matrix format, which we call CRAC, which stands for compressed rows aligned columns, and the idea for it is actually quite simple. Take the principle of the column of the row pointers array in CSR, which points to the start of each row, and apply it also to the column index array, which is now called the column alignments array. So the first index in the tuple of the column alignment array points to the location, defines the index number, so the actual column in the matrix of this of the data, and the next index points to its location in the values array. What's the point of doing that? Well, if you have something like HBFEM, and you have higher polynomial powers, you can see here on the left a chart that maps compares the size of the column index array in CSR with CRAC. And if you go to the direction of polynomial power 8, you get 1/10 of the size. So we have a massive reduction in data size. And this is important because finite element applications on sparse matrices usually have very large matrices. So we want to save memory wherever we can. The same applies for the dimensionality of the problem. If the problem is a scalar problem, like the Poisson equation, it's not very efficient. It's a bit bigger. But if the problem is something like a shell element or a plane element with multiple dimensions of the problem, then again, we get a very, very good reduction factor. So the next data structure we need is some sort of index map from each finite element to the global sparse matrix, which is give an example where we have very simple approach, just number them and save them in some array. Another thing we can do is make this more compact. We look for sequences and then we give the start of the sequence and its length. And this is useful because we can use this afterwards for vectorization. And last but not least, we would like to work in parallel. And the question is, how do we do this in parallel? So the common approaches to parallelism of the assembly of finite element applications are usually to do coloring or divide and conquer. Here we opted for atomic assembly. And what we did here is we would like to have some sort of synchronization mechanism embedded into the sparse matrix format. So we can lock rows and unlock rows whenever we assemble data into them. And in order to do that without to increase the data size of the sparse matrix format, we introduced here a new type of lock mechanism called a spin integer. This is essentially a spin lock, which the locking itself is by changing the sign of the integer. Since the integer is in the row pointers array and only points to data, to get the actual location of data, all we have to do is take the absolute value. And this is what we did. And then we can move on to the actual Rust implementation and the communication with Python. The project itself is called Grace, and it's distributed in PyPy as a built binary. Okay, so this is how the crack format actually looks in Rust. We have the data. It is contained in the covec vector, which is essentially concurrent vector, which allows for unsafe parallel access to indices, which we will make safe via synchronization. We have the p rows array and the p columns array, which again points to gives the index and the start in the values, that is the data array here. Now the assembly can be done in parallel. We use Rayon for parallelism. We take the elements array, which is essentially an array that contains all the elements in the finite element mesh, and we iterate over it in parallel using parallel chunks. We do that because we need some other things like sure complement and some communication with the Python that we need here. But we do that in parallel chunks, and then we can assemble. So each element gives its local matrix to the global sparse matrix here, and we can assemble it. And in the assemble instruction, this is where the synchronization takes place. Namely, you see here, I don't know if you can see my mouse. I hope you can see the mouse. You see here at the start, we get from the sparse matrix the location of the row in the column index array. And we do that by locking the row, and we will unlock the row at the end. And when the row is locked, we can assemble into it without worry that we have some sort of data race. And here we also use directly the type of data structure that we have, the element stopes array, which is the local to global index map. We can use the fact that it saves sequences to use a vectorized instruction. This is what you see here in the else statement, vec add. It maps to dynamically sized vectorized instructions. So the last step, the last thing we need to solve this somehow. Luckily, the ULEX micromorphic model is symmetric positive definite, which means we can use the conjugate gradient solver. So the main ingredient in the conjugate gradient solver is the sparse matrix dense vector multiplication algorithm. How do we do that in parallel? Well, we did this over the shift right assignment here, just because of notation. We use the target vector, with which we write, and we can iterate over its rows in parallel and write to each row the scalar multiplication from one row of the sparse matrix with a column, with the entire vector. So again, because the crack format itself saves sequences of columns, this is the column alignments array. It tells you when there is a contiguous sequence of columns in memory. You can do this with the vectorized instruction vec., which maps to dynamically sized scalar products of essentially slices.
If you could quickly just sum up your 7 minutes about.
Thanks. Okay, so this is the interaction with Python with Py3, which has defined a Nexus class, which is a Py class over Py3, and it's wrapped in the domain class in Python. And then we can essentially write some scripts for it using lambda instructions, just call essentially the background Rust code. And here's a small example: linear elements on the left, higher order elements, cubic elements on the right, to approximate a sign function essentially in a beam. And this is a better approximation with higher order elements. So thank you for your attention. And here are some references. Be glad to answer questions afterwards.